Hello. So today we're going to be looking at Ka values, Kb values, and making sure, first of all, that you can write equations that match Ka values. So if you see one of these Ka values on the chart, on any chart, you need to be able to write the equation that matches what that value is. So for example, sulfurous acid. This has a value listed on the table. The value listed on the table is associated with this thing giving up a proton in water. This is just water. So that's your expression, or that's your equation. All right, so you pick any of these. You look at formic acid. Formic acid, H. You got that? So for writing an equation for what's going to match the value on the chart, we start with this. It's going to be acting like an acid in water, and we're going to get H plus. Look at that. Any of these. Carbonic acid. Carbonic acid. All right, we get that. Then you need to be able to write the expression. So we'd write something like Ka equals you get that. So every Ka expression that you're going to write is going to have H plus in it. The H plus is going to be in the numerator. Your weak acid will be in the denominator, and its conjugate base also in the numerator. So that happens every time. That should look like a K. Like if you just saw that, that should look like, oh, that's Ka. I can look up, I can find some value for that, or I can calculate it if I'm given these some concentrations, some information. So that's that. Matching Kb values. Same thing, we have this list of weak bases, and you need to be able to write the equation that matches that value. So I could write the value here, maybe just to make sure you see 4.4. So for carbonic acid, the value that we're given is 4.4 times 10 to the negative 7th. This gives us some idea of how much of what's in the numerator we're going to see. This value is pretty small. They're all pretty small, but H2SO3 is much higher, so you get more protons. Anyway, so writing equations that match Kb values. So you just pick something, say, all right, we have a Kb value for it. So if we have a Kb value, we're always talking about sticking a weak base in water. And for this, we write the water. You could write the water over here, plus water, and then you'd have H3O plus. That's up to you if you want to do that, but I usually don't. But here we have SO4 2 minus plus H2O. And if this is acting like a base, it's going to pull a proton off of water. So you get OH. You get that. So again, you look down the list, you find some other nitrate. You got NO2. You put it in water. You get OH. Right, just automatically, you just go down whatever list you want, HPO4. Okay, so, and then you write it, and then you write your KB. expression. So Kb, we've got products over reactants, and we don't write water. So with a Kb expression, you're always going to see hydroxide in the numerator because it's a product. We're talking about a weak base reacting with water. So we always see hydroxide there, and we see the weak base that made the hydroxide. We see the weak base in the denominator. We see its conjugate acid in the numerator. So that's something we always see when we're writing these expressions, right? So for Kb expressions, you always see OH. For Ka expressions, you always see H+, and that's just something that needs to really be automatic. Now on to an actual question. So here's what we're looking at. Look at number 1. We've got a solution of formic acid mixing with sodium hydroxide. We need a net ionic equation. We got a Ka value. All right. So I'm going to erase this side. You'll see why in a second. Alright, so first thing is you need a net ionic equation for the reaction. Anytime you're doing net ionic equations, make sure your weak acids or weak bases stay together. We have a weak acid, so we just write it. We have a strong base. So for this one, we're going to get rid of the spectator ion, sodium. We're going to write this. Well, this thing is going to pull the proton off of formic acid, H2O, and formate. So, alright, so it's our net ionic equation. This should start to look familiar, right? You see hydroxide there. So the part B asks you to calculate the value of the equilibrium constant for this reaction. So if we were going to write an equilibrium expression for this reaction, we would get rid of, don't worry about the water. That would be our equilibrium expression for this reaction. So this needs to look like something. You need to see, okay, we got hydroxide. Hydroxide's in the denominator. That's the opposite of a Kb, right? With Kb expressions, we had hydroxide in the numerator. So that should trigger something. Well, actually what we see here is we've got hydroxide in the denominator, and we've got a weak base in the numerator. That's exactly the opposite of what we had over here with hydroxide and the weak base. And the weak base's conjugate acid is right here. So in the denominator along with hydroxide. So what this should look like to you is 1 over Kb. And so if you see hydroxide in it, especially in the denominator, well, in the denominator, you're going to have the inverse of Kb because it's the reverse reaction. So, all right, so we've got 1 over Kb. Now they don't give you Kb, they give you Ka, but we do know that Kw equals Kb, so we can rearrange, and so Kb equals that. So this expression, this K value is going to be this flipped. 4th, kW is 10 to the negative 14th. So this is going to have a really high value. This is going to go to completion. You know, every bit of this that can react will react because the value is going to be so high. And you can calculate the exact value. So our next job is to calculate the pH. Well, if we're going to calculate the pH, we need to see how much of this stuff actually reacts. Let's see. We have 0.2 liters. 0.2 liters times 0.4 molar is 0.08, right? Number of moles for formic acid, 0.08. And here we got 0.3 times 0.15, so 0.045. All right, so 0.0450 molar hydroxide. So you can see the hydroxide is the limiting. That's going to go down to 0. And the formate is going to start off at 0, and that's going to be plus. So we have a number of moles of formic acid, a number of moles of formate. It might be hard to see, I'll just put a box around it. And so now we can calculate we want to calculate the pH. We're given Ka. So this is the reaction that takes place. But what you need to keep in mind is that after the reaction takes place, there's not going to be any more hydroxide. This reaction's done. And so then what we have is weak acid, weak base. And those are in the container. 12 minutes. So I'm just going to write a Ka expression. Let's see. I'm going to write Ka because that has the H plus in it. I'm trying to find the pH. I know if I'm going to write a Ka expression for a weak acid in water, I would have the acid on the reactant side and in the denominator. And I'd have the weak base in the numerator. So that's my Ka expression. I could just rearrange this. So Ka times the concentration of formic acid divided by the concentration of formate equals the H plus concentration, and then you can take the negative log of that. So that's, I guess I could actually do that. And here we have concentration in the numerator and denominator. You see that? Numerator and denominator, so we can just use the number of moles of each of these and just plug them in, multiply by Ka, and there you have your H plus concentration. Hope that helps. Bye-bye.